classical mechanics, continuing along, doing non-inertial reference frame. So when you have a non-inertial reference frame, a frame that's accelerating, you have to add these fake forces into it. So I already did the derivation of just plain linear acceleration. I did the derivation of Coriolis force, centrifugal force for a rotating reference frame. So let's do a problem, and I took this from a book, but it's a good problem, and I'm going to do it two ways. So let me tell you the problem. I'll solve it one way. I'll solve it the second way. You know the second way is going to be Python. You know that. Okay. So imagine that we have the Earth, because we have the Earth, and there's a tower with a ball on it. We're going to drop the ball from rest at the top of the tower, and it's going to hit the ground. And we want to calculate the deviation of the ball as it falls due to the rotation of the Earth. So the ball is dropped at rest with respect to the rotating Earth, not with respect to nothing, because it's going to be moving with the Earth and the Earth is rotating. Okay, so I'm going to solve this with an approximation, and then I'm going to solve it with Python. I already told you that. Okay, so here's my rotating Earth. It has an angular velocity that way. My object is on a tower of height h above the surface of the Earth, and then we have this angle theta from the horizontal, from the vertical axis. And so, you know, I'm in Louisiana. I'm at a latitude of 30 degrees, so this would be 60 degrees from there. That's that angle. And then we have the radius of the Earth and all that other stuff. So in the rotating reference frame, I have three forces on the ball after it's released. So I can write this. F net is going to be the gravitational force minus or plus the centrifugal force plus the Coriolis force. Now, in my rotating reference frame, I can pick my coordinate system. And just to make things easier, I'm going to pick this as the z direction. If that's the z direction, I'm going to pick this as the y direction. And then the x direction will be into the board. Okay. So in that rotating reference frame, it's not at the origin, but that only matters in certain situations. In particular, it would matter for the centrifugal force, but we actually don't need to worry about the centrifugal force. Let me write down a couple things. Okay, first, let's write this angular velocity vector, omega, in this coordinate system. Okay, so in this coordinate system, if I move that angle right there, then this is the angle theta. So I can write this as 0 x hat. It's not in the x direction. Make that a little smaller. Omega is 0 x hat. In the y direction, it's going to have a plus omega. So this is the magnitude of the angular velocity, sine theta y hat, right? Because here's my y component of the angular velocity vector, and it's the opposite side of that triangle, so we're going to use sine. And then in the z direction, it's going to be plus omega cosine theta z hat. So let's go ahead and write my two definitions for the centrifugal and Coriolis force. So I should note G is going to be 0 x hat plus 0 y hat minus G 9.8 z hat, right? Because z is my vertical direction. That's G. And then finally, the centrifugal force, F cent. We can calculate that as m times omega cross r cross omega. That way we get a vector for that. But this is going to be pretty small, and I'm going to tell you something about this in just a second. And then the Coriolis force, F core, is negative 2m omega cross v. Okay, so the centrifugal force only depends on the position r. And that would be in this picture. Let me just draw a little bit bigger picture. So here's my axis of rotation. Here's my object right here. The Coriolis, the centrifugal force is going to be pointing away from the axis of rotation, so it's going to be that way. And then we have a gravitational force, mg, that way. Now, how do you know the direction of up and down? How do we know the direction of our z-axis? Normally what I would do is I would take a string and hold it up and let it hang down. And then that's the direction of down, that's the direction of up. A plumb bob. However, the plumb bob is on the rotating Earth, so the plumb bob actually shows the direction of mg plus that. So it actually is going to tilt a little bit away. And that's how we define our up and down. Well, on top of that, the Earth experiences this centrifugal force too, so it actually isn't a complete sphere, it actually bows out. But the end of the story, we can't really tell which way is up and down with that force, unless you look at the stars. It's kind of hard. And that force is actually pretty small, because omega, the value of omega, I got twisted up there, omega is going to be 2 pi radians per day. So it's actually a pretty small value, and then I square that, that makes that a small value. So at the end of the story is that I'm just going to ignore that for now. I'm going to not ignore it later, and we'll see if it was a good choice, right? So you always want to make a decision, do something, and then go back and say, was that a good idea or not? And we'll see that that was an okay idea. So I don't have to worry about this force right here. That's the end of the story. The next thing I want to point out is that I can write the net force, and we're going to calculate this in a little bit. The net force is mass times acceleration. And that's going to be equal to, now I just have mg plus the Coriolis force, which is going to be minus 2m omega cross v. Now, mass. I can just cancel the mass. I don't even need the mass. I don't need to know the mass of the object. All the forces depend on the mass the same way, so it doesn't really matter if I change the mass of the object. So I don't need to know the mass. So I can actually just say the acceleration is going to be equal to g minus 2 omega cross v. Oops, I missed the cross. Okay. So that's where we're at. That's the equation we're trying to solve. I want to go ahead and write the velocity in Cartesian coordinates, and I want to find this omega cross v. That's going to be pretty important. But all that stuff I think I can delete now. Delete with my deleter. Okay, so let's delete all that stuff. So here's what I have. Oh, I shouldn't have erased that. So I do have omega is 0 x hat plus omega sine theta y hat plus omega cosine theta z hat. Now my velocity in Cartesian coordinates is simple. X dot x hat plus y dot y hat plus z dot z hat. And just as a reminder, I'll put it over here. X dot, we use that dot notation to represent the derivative of x with respect to time. So that is vx. That is my x velocity. So that's what that dot notation means. I have my two vectors. I can do the cross product. Let's do the cross product. I'm going to write out the whole Coriolis acceleration. I call it A core is going to be equal to negative 2, the mass canceled, omega cross v. So I can write that as the cross product of x hat. I can make right as a determinant y hat, z hat, and then I'll put the negative 2 over here. My omega values, so it's going to be 0, omega sine theta, omega cosine theta, and then my velocity values, x dot, y dot, z dot. Now I just need to take the determinant of that matrix. So I get A core equals negative 2 times, okay, now I'm going to expand about the x component. So now I take the derivative of the determinant of the submatrix. So it's going to be this times that minus this times that. So I get z dot omega sine theta minus y dot omega cosine theta. That's going to be, they're all going to have the negative 2, x hat. Now I can do negative 2 times the y hat component. So now I'm going to expand about this. Now remember, when you expand about that y component, you have a negative there too, so you go backwards. So it's going to be omega cosine theta times x dot, omega cosine theta, times this, 0, and that's going to be y hat. And then finally I have negative 2. Let's do the z hat direction. So here I'm going to have z hat cross that out. I get 0 times y dot minus this times that. So minus x dot omega sine theta. That's a theta, z hat. So now I have my correlation, my acceleration due to the Coriolis force. And then I have my acceleration g is, let's just put that as negative g z hat. Okay. Now, I have the acceleration, this plus this, and I can also write my acceleration as x double dot x hat plus y double dot y hat plus z double dot z hat. And I can say my x component of this acceleration is the sum of the x components of these two acceleration vectors. And there is no acceleration vector right there. So I can get a single equation for x. I erased my gravity, but you knew what that was. So I get x double dot equals, okay, there was no component in the g, but I do have this. So I get negative 2 z dot omega sine theta plus 2 y dot omega cosine theta. So that's a differential equation. It's no longer a vector. I can do the same thing for the y double dot. Y double dot, okay, again, doesn't have a g component, so it just has the correlation, the Coriolis force. So I get this, negative 2 x dot omega cosine theta. And then for the z direction, that one does have that negative g component in there. And then I have this. So I have a negative times a negative plus 2 x dot omega sine theta. Okay, so now I can erase all this stuff. So now I have my differential equations. I have 3 second-order differential equations, x double dot, y double dot, z double dot. But there's a problem. The problem is that x double dot depends on z dot and y double dot. Y double dot depends on x dot. Z double dot depends on x dot. So we're kind of in a tough situation. One way to solve this is just to say, let's make the approximation that omega is very small. So 0 is, let's say, omega is approximately equal to 0. That's my small. Okay. If that's the case, then I have x double dot equals all of that times 0 and 0, so I get 0. Y double dot equals, oh, I got omega, so it's 0. Z double dot, okay, I have negative g and then 0. So yeah, that's just plain free fall motion. Let's go ahead and solve it. Okay, I'm going to release this from rest. So let's just say v at 0 equals 0. Okay, I'm going to release it from rest, and it's going to have an initial position r equals h z hat. So I'm releasing it in the z direction, but the x and y coordinates are 0, which you don't have to do that, but it's just going to make it a little bit easier. So let's solve this equation. So I'm going to integrate this once. I get x dot equals a constant, right? Because I get 0t, and then I have a constant. And if I release it from rest, then at time t equals 0, this is 0, so c has to be equal to 0. Now let's do it again. X as a function of time is going to be a constant, but that's going to be also 0. So it's kind of boring. And the same thing's true for the y. So this is going to be y dot, and this is going to be y. Big deal. Over here, if I integrate both sides of this equation, I get z dot equals negative gt plus a constant. But again, I released it from rest, so z dot at 0 time t equals 0 is 0, so c is 0. And then I integrate again, and I get z as a function of t is going to be negative 1/2 g t squared plus a constant. And at t equals 0, this is h, so c is going to be h. I went over that kind of quick because I figured we'd done that a bunch of times. Okay, so let's put that over here. Z equals negative 1/2 g t squared plus h, and z dot is negative gt. That's important. Okay, so we have a 0th order solution. That's what that is. I can erase this. Now, let's go back and rewrite our second order differential equations with our new velocities. X dot 0, y dot 0, because we have those derivatives in here. So that becomes, this equation now becomes x double dot is minus 2, and then I have z dot's negative g, so I get plus g t omega sine theta. And then I'm going to put in for y dot, but y dot 0. So that's 0. And then I do the same thing for y double dot. It's going to be negative 2 x dot 0, so I just get 0. And then I put this in for z double dot. It has an x dot, and so z double dot still just negative g. So the only thing that changed was our x equation. Well, we can solve that. I can solve that, right? This one's not too bad to solve. I can integrate both sides. I get x dot is going to be equal to 1/2 times 2 times g t squared omega sine theta plus a constant. And again, at t equals 0, if I put in t equals 0 there, the velocity is 0, so c is 0. And the 2's cancel. Now I can integrate again. X is going to be equal to 1/3 g t cubed omega sine theta plus c. But at t equals 0, if I put in t equals 0, c has to be 0 because x is 0. So that's 0 too. But there, we have it. That's my x position as a function of time in this approximation. Okay, let's calculate the deviation if it falls from some height. H is 100 meters or something like that. Okay, so let's say h is 100 meters. Let's calculate x. Now, I need to first find how long it took to hit the ground. So I need to find t. Well, I can go up here and solve for t, right? So z, I'll write it z as a function of t is going to be negative 1/2 g t squared plus h. And I want to find the time it takes for the ball to get down to here where z is equal to 0. So 0 equals negative 1/2 g t squared plus h. I'm going to move the h to the other side and cancel the negatives. Now I can multiply by 2 over g, and I get t squared, 2h over g. So t is the square root of 2h over g. The same as free fall. There's no magic there. Now if I plug that in over here, I get x equals 1/3 g t, right? So I'm going to put this in for t, but I have the square root. So I get 2h over g to the 1/2 times to the cubed, so to the 3/2, that's a 3/2, omega sine theta. So that's my deflection. Yeah. Okay, let's go ahead and calculate this. Now, of course, you're going to have to do a bunch of clickety-clickety on your calculator. I'm going to go ahead and do it in Python because Python's a great calculator. And then we'll switch this to a numerical calculation just for comparison, which will again use another assumption. And I'll go through that steps in just a second. Okay, so here we are, Web v Python, just going to enter my constants. So the first thing I want to do is to calculate omega. I'm going to call omega the scalar value of that, and it's going to be 2 times pi divided by a day, right? And so let's calculate a day in seconds. A day is going to be equal to 24 times 3600, right? Because there's 24 hours in, yeah, I know it's a solar day, but don't worry about it. You can change that if you want. You can make it sidereal or whatever, or synodic, whatever you want. I get those two confused. So there's my omega. Let's just print that out just to make sure we know what's going on. Omega equals omega radians per second. Okay, I'm pretty sure that's the right answer. Okay, now let's put in G is 9.8, H is 100, and then I need theta. I told you I was going to do 60 degrees, so 60 times pi divided by 180. I need it in radians, but I think in degrees. GH omega sine, that's it. Okay, so let's just go ahead and calculate t. We don't have to, but just for comparison, T is going to be the square root of 2 times h over g. Let's print that out. We're going to need that later. T. And then let's print out x. X is going to be equal to 1/3 times g times, I already have t, so it's t cubed. I'm just going to put in t cubed. I don't have to recalculate it. Times omega sine theta. And let's print that. This is x final. And let's run it. Okay, so it took 4.5 seconds, fine, and it deviated 1.9 centimeters in the x direction. And we said there was no deviation in the y direction, remember? Okay, let's do the problem the second way. Let's switch back and talk about what we're going to do. I'm just going to delete all that stuff. Erase. Okay, let's do this a different way. And I'm actually not going to assume a zero centrifugal force. What I'm going to do is to calculate the force on the object. So the force on the object is going to be equal to mg plus m times omega cross r cross omega plus minus 2m omega cross v. That's it, right? And again, we can divide by the mass on both sides and get the acceleration if you want. I'm going to go ahead and do that. So the acceleration is going to be g. Actually, I'm going to do this. Why? I got a chalkboard. I can just do g, and I can literally just erase those things. I can do that, right? Okay, that is a vector. Now the problem is that the acceleration depends on both the position and the velocity. And I just realized that this r is going to be kind of complicated. So I think I'm just for now, I don't want to make things messy. I already said that would be okay to ignore. I want to ignore that. Is that okay? Okay. So we're just going to deal with this, make it simple. Because I already had a 22-minute video. I got class at some point, right? I'm going to have to go to class in an hour. So if the acceleration depends on the gravitational field, that's fine. But it also depends on the velocity. And the acceleration changes the velocity, so it's not an easy problem. And we have multiple directions here. So again, what we'll do is we'll say, okay, delta t is 0.01. If I pick a time interval that's short, I can assume that this value is constant over that time interval, and then I can use my velocity update formula. So I can say the acceleration is the change in velocity with respect to time. And if you've seen any of my videos, you know I've done this derivation a billion times. v2 minus v1 over delta t. So this is the velocity at the beginning of the time interval, that's at the end. So I can solve this equation for v2. v2 is v1 plus a delta t. Now I can do the same thing by assuming the velocity is constant. I'll actually call it v2 because that's technically what it is. And that's the change in position with respect to time, which is r2 minus r1 over delta t. And I get r2, r1 plus v2, because I just calculated that, delta t. Now I know the position, the velocity at the end of that time interval. I can go to the next time interval and do the whole thing again. So that's what we're going to do. So to do this, I need my gravitational field vector in the z direction. I need my angular velocity vector, which I already wrote that out before. I mean my initial velocity, my initial position. Okay, let's go to Python and make this happen. And we can compare and see if we get the same thing what we got before. Computer, here we are. Okay. So I'm going to start off with some stuff. So I need my omega vector. I'm going to call that capital omega. And that's going to be the vector 0 omega lowercase sine theta. That's what I had before. Omega cosine theta, remember? GV, I'm going to write my GV as my velocity, my gravitational field vector. It's going to be the vector 0, 0, negative 9.8. I need my position, my position A of R is going to be equal to vector 0, 0, h, the same value of h I used before, so I don't need to put that in there. And then my velocity, v, is going to be vector 0, 0, 0, release from rest. I already used the variable t, but it's fine. I can rename it to 0, and then dt is 0.01. Okay. I think I have everything I need. A graph. Let's make a graph. G1 equals graph. I'm going to plot the z position versus time first. Graph x title equals time. Y title equals, what does y title equal? A z. And let's put a width, 400, height, 200. And then let's call this fz equals g curve, color equals color dot blue. Okay. Now I'm going to make a loop while r dot z is greater than or equal to 0, right? Because I want to let it fall until z gets to 0. And that's a great way to do that time. Now, I have to do r dot z because r is a vector. I need the z component of that vector. Be careful with while loops like this because you can get yourself in an infinite loop. If I started with a negative z, it would go, or something like that. It could go on forever. Okay, I'm not going to animate it, so I don't need to do a rate statement. The first thing I'm going to do is just calculate the acceleration. A is going to be negative gv, the gravitational field vector. No, I'm sorry, not negative, plus. Right? I've already included the negative part in that component. And then the Coriolis force is going to be minus 2 times cross omega v. So cross is a built-in function in WebV Python that takes a cross product between two vectors. So it's simple. That's it. Now I'm going to update the velocity. V equals v plus a times dt. And I'm going to update the position. R equals r plus v times dt. And then I'm going to update time. T equals t plus dt. Now I'm going to plot it. Fz dot plot t r dot z. Let's see if it runs. I didn't even save it. That's just me asking for trouble right there. I guess I should save it. Drop. See, I can't. I have it zoomed in too much. Ball. Okay, that's fine. I did it. Okay. Save. Okay, now we can run it. There we go. Okay, so let's go ahead. It looks fine, right? It starts at 100. It gets down here. It looks like a parabola. It should be very close to a parabola. Let's go ahead and print out that time just for comparison. So after this loop is all done, I'm going to say print t equals, and let's print the time again in seconds. Oops. Seconds. And just as a comparison, it should be at least close to the value that we had before. So I got 4.51, 4.52. Okay, close, good enough. Now let's plot the x position as a function of time. So to do that, all I need to do is to make another graph. Let's make a graph 2. Let's copy all this stuff. Call it graph 2. And let's make this x. And fx equals g curve, color equals color dot red. And then down here, I'm just going to plot that. Fx dot plot t r dot x. And let's print out the final position because we did that before. Print x equals x meters. Okay, so the curve, it's hard to tell anything useful from that. What I really can do down here is to look at this. Here I have x's 0.0189, and before I had 0.0189. So they're exactly the same. Interesting. Very interesting. Let's just, for fun, let's just plot the y velocity, the y position as a function of time. So up here, I'm just going to change this to y and this to y. I don't even have to do that. But and then down here, I'm going to change this to y, and let's print y. Let's just print the final position. R equals r meters. Okay, so you see here that there is a y deflection, and we do have a final y position, but it is super, 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 super duper whooper tiny, okay? But why is it not 0? Well, in order to understand that, we need to go back and think about our previous equations that I erased. I had, in my first approximation, I had y dot was 0. But y dot's not 0, right? Y double dot depends on x dot, and the x dot is not 0 because it moved. It changed speed. So there is a y dot velocity, a y component of the velocity. So there will be some deviation in the y direction. So this method includes that deviation in the y direction. The other method doesn't. Oh, now I have two different. Why do I have x? Oh, that's why I printed x. No wonder they're the same. That was my fault, and you should have caught that. So we do get a slightly different number right here. I was printing out x instead of r dot x. And so it's a slightly different calculation. Now, for the most important question, which of these methods is better? I think they're both good, and they both have their places. I kind of like the numerical version better because it's still an approximation, right? We're approximating constant accelerations over time, but it incorporates more pieces in there. We could add in that centrifugal force too. Probably what I would do for the centrifugal force, if you want to add that in there, just add it in as a constant value, and because the position, the distance from the Earth, center of the axis of rotation doesn't really change anyway. But the fun thing would be to take this and expand it to something interesting. Let me switch back to the board. I want to show you another problem that I may or may not do. I'm really just doing this for myself. Imagine now I have a smaller object, and it's an asteroid, and I start at some other distance, but it's rotating a lot faster. Maybe it rotates once every 3 hours or something. I'm picking something like that. And in that case, you can't make those same approximations that we had before that omega was small, so you couldn't do the first method. But you still could do the second method, and I indeed will. And I just said I will. Okay, I got to do it. And so as this thing falls down, we can model the motion two ways. We can model the motion in the system of the rotating asteroid, and then we can look at it from the outside too and see if those two things agree. It'd be kind of fun, so I'll probably do it, but I don't know when. But I did it. I really want to move on to the next chapter in our course here, which is Lagrangian mechanics. I'm very excited about that. So that's going to come up soon. But that's that. I'll give you a link to this code down below. Hope you enjoyed that later.